Bismillahirrahmanirrahim. Greetings. This is going to be the fourth lecture in a series of video lectures that I'm uploading discussing about the concept of inverse functions. Now, in case if you may have not already watched the first three, I strongly encourage you to do so, and I have provided the site link of those videos in the comment section. Now, in this video lecture, I'm going to discuss about the inverse of exponential function, and which is a little bit different than others. Okay, enough for introduction. Let's get started, shall we? Now, y equal to 3x, with algebraic manipulation, this is equivalent to say y over 3 equal to x, and they will have same graph. When I say by graph, I always repeat that one. I have said it in the previous lectures. Graph means in 2D set of ordered pairs. And when we usually think about graph as analytical geometry graph. But graph means, again I repeat, is a set of ordered pairs. The analytical graph that we see is a geometrical representation of that. So in order to distinguish between them, I do mention analytical graph and geometrical graph. Now, here they both will have same they will have same analytical graph. The rule of correspondence between x and y has not been changed. The rule of correspondence between x and y, they are what? They are preserved. This is just another way to present that one. As I mentioned in the first lecture, 3 plus 2 equals to 5 is equivalent to 5 minus 3 equals to 2. Two different operations, but equivalent with respect to the equality. The very same goes through here. Two different operations. This one is multiplication, this one is division, but the concept is same. They are saying same thing, they will have same graph. The very same goes with this one. But this one, the algebraic manipulation was a little bit involved. This one was very explicit. We could write very easily from this to get that one. This one we had to raise both of them to the power of 1/2. So we were dealing with exponent, numerical exponent to come to this. And this are what are again equivalent. They are paraphrase of one another. You follow me? So now we come to the exponential function, to this one. Now what can we do this one? Now I have y equal to the x. Now how can I write the equivalent form of this as I have done it with this? And I cannot do the same kind of algebraic manipulation that I had done for these two. The first one was the easiest one. The second was a little bit involved. Oh no, this one I'm puzzling. Now, then I come to the idea that what I did to this, can I also do it to this one? Meaning raise both sides to the power of 1 over x. So I come up with y equals 1 over x equals to 2. But this is a little bit strange looking to me, because I know when x is a integer in most of the time, I know how to interpret that one. But when x can assume different values, different real numbers, let's say, of course, except 0 in this case, are they same or not? Now, I have tried, we come to that, and with a chart that I got, analytical graph of that, I end up to be, yes, it is correct, but this needs mathematical interpretation, mathematical proof before it is accepted, and that for the time being, we just call this one as a conjecture that we know is working for the time being. But that is beside the scope of this lecture, so I cannot go for that one. Okay, then, if you like to take a note, you are welcome to that. Let's go to the next now, shall we? Now in this one, I'm interchanging the rule of correspondence of x and y. I'm interchanging. Now, y equal to 3x, when you interchange the rule of correspondence, you end up with x is equal to 3y. All right? The same is true for this one. Y is equal to x squared. To change the rule of correspondence between x and y, x is equal to y squared. Now, the very same goes here also, comparing to them. Y equal to the x, x equal to the y. So if I sketch this one and 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 this one, I will see something notice of that. And that is what we call this one to be inverse of that. But what do we mean by inverse? What does mean by inverse? We have already discussed about that, but we are going to talk about that also again later. What they mean by inverse. Okay, so you are welcome to take a note. Now I go back to what I said about y to the 1 over x to be equal to 2. A chart that I have made for that. Okay, y equal to the x. This is the, I took the elements from the analytical graph of that, and I made this chart, and you can see it. We have gone, this is easy to comprehend. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8, and so on and so forth. You can also put negative numbers. Now, I went to this one, and selected different values also for x. If x is 0, is not defined. No. If x is 0, is not defined. Here x is 0 is defined, but here is not. Then I plug other numbers, and I end up to be very similar chart to this one. As I already mentioned, I'm puzzling this one. For the time being, it's a conjecture for me. But with the data that I select, with from the analytical graph of that, I pick numbers, integers, negative also. I end up to be, yes, this to be a kind of paraphrase of this in a sense, to be same chart. Now, I change the rule of correspondence between x and y, and I write x equal to the y, all right? And I came back with this chart. Again, this chart coming from what? From the set of analytical graph of that, set of analytical. So I picked some of those pairs out, and I came back with that. But you can plug numbers and you see it for yourself. And when you compare this set with this set, this cross table with this cross table, this cross, this cross, let's call it, I don't know, crosses because they are familiar with that. This and this are what are exactly x and y has been switched, as we have done it in the previous lectures. And the order pair x and y have been interchanged, as you can see that. You can see it for yourself. Okay, now we come back to the graph of to the x and interpret the inverse of that with respect to the rotation and reflection. So far we know, as I already mentioned, there are other ways to do it that we are going to discuss it later on. Okay. Now, this one is the graph of y equal to 2 to the x. So you can plug numbers positive and not negative, and this graph comes out of it. And most of you are maybe already familiar. Now, what we have learned before, we know that it holds for every relation. I did give you a guarantee, and that is if you rotate it 90 degrees clockwise or counterclockwise, then reflected about the horizontal axis, what you get is the inverse of that. The graph of is inverse of that. the geometrical graph of the inverse of that. So we know how the geometrical graph of inverse of 2 to the x looks like with the method of rotation and reflection. All right? Now, we go to this one, and I put that one, how the graph of the inverse looks, if for those that they like to somehow take notes. So this is obtained by what? By the graph of 2 to the x with the method of rotation and reflection. 90-degree rotation, clockwise or counterclockwise, 180-degree reflection with respect to the what? Horizontal axis. Okay, now we come with the 2 to the inverse of the function that I just mentioned it, which is x equal to the y. Now we want to sketch that one, not with rotation and reflection, not with the technique of rotation reflection, but we want to just plug a graphic with respect to plugging points. Oh, here it is the chart. Here is the chart. We call it cross table. Now with respect to this chart, if you plug numbers and points, you will find this graph to come out of it. So we have already seen that. We know this is the graph of x equal to the y, which is, we are calling that inverse of that, and then we will discuss again what do we mean by inverse. So that is inverse of y, 2 to the y equals to 2 to the x. That is the graph of inverse graph of y equals to 2 to the x. Now, I have put both of the graphs, the geometrical graph of them, on the same horizontal axis for comparison and also for analysis in a sense. This is the graph of y equal to 2 to the x. Y is a function of x, and the rule of correspondence of that is y equal to 2 to the x. This one, we want to write it into the form of y equals the function of x. We are going to, that's exactly what the goal is. Now, here, if as I did that exactly for the previous lecture with the parabola, if I pull this one toward this so that the vertical axis of this graph superimpose on the vertical axis of this graph, and they are sharing the same horizontal axis, then there is something nice comes out of it, that we are going to look at it, contemplate, think, reflect, and see what we can see from that before we go to mathematical proof for that. So in your imagination, can you imagine when I pull this one out so that this vertical axis superimpose on the top, how the graph will look like? I give you a few seconds, you think about it. The picture should take form in your mind before I do show it to you. Okay, so this is what when we push this one or pull that one toward this will be the picture that we will be seeing of it. Now stand by and see what you will notice from that. Look at it, think about it. We notice that these two graphs are mirror image of each other with respect to this line, which is 45-degree line, to be mirror. You know, if I'm standing next to you, I'm in reality mirror image comparing to you, because my right hand is your left hand, all right? Now, when I'm standing in front of you, the mirror will be, I'm a 3D, is that right? But the mirror will be a 2D, will be a plane. So since this is a plane, therefore we are expecting the mirror to be a line, one dimension less. 3D was a 2D, the mirror was. Now 2D, the mirror we are expecting to be a line. And that's exactly is happening. Look at that, the mirror is indeed a line which is f1d. Now these two graphs, the graph of y equal to the x and the graph of x equals to the y, end up to be mirror image of each other. In one sense they are equal, as you already noticed. I didn't distort this one, I just rotate and reflect. On the other hand, they are one mirror image of each other. Now let's see what that means also as far as the inverse is concerned. Now, what do we wish? Now, our goal is to write x equal to the y into function notation, because we are not kind of comfortable with that. We want to put it in function notation because we always deal with function. Or in our mathematical endeavor, we always deal with function notation. Okay, then I have written that one if you like to take a notes for yourself what we wish to do. And that is exactly because we want to write this one, x equal to the y, into the function notation, and it is not as explicit as the other one was. Like the other one, like y equal to 3x. That was explicit, we could easily change it into the function notation, but this one is a little bit different. And that is exactly what the symbol of log comes from. So log is a symbol, is not a difficult thing to think. You can see there is really nothing into the log. All right? Now, let me go further for that and see what I mean. Okay. Why? I like to read it the way I told you to read it. Don't say, I have written y equals to f of x equal to log of x. I have written, but don't read it the way it is. Read it the way it looks to you. Read it that way. Y, read this equality as is. Y is a function of x, then this equality read it as with the rule of correspondence, the rule that corresponds x and y, to be log of what? Log of base 2x, which means y equals to log base 2x. Now what does this symbol log comes is give us the notation that we need to have. So give us the notation of function notation. So here, this is exactly same as this one. It's just two different representation. That's the best way to say it. Two different representation. Sometimes this is good to use for interpretation, depending on the concept. Sometimes this one is better to use for the interpretation. I'll come back to this in the end also to say a few words. So again, one more time, I repeat myself. This and this are identical. They are same. They are saying same thing, but in different notation. And many things in mathematics we use as a different notation. Like, for example, we say x to the 1/2, we use a square root of x. And sometimes x to the 1/2 has advantage for us to use. Sometimes a square root of x symbol has better advantage to use, depending on the topic and depending on the manipulation that we need to make. All right? So symbols are not created for giving a student hard time, and symbols are developed with a very prominent mathematician for the better convenience and better conceptually understanding the subject in a sense. Now, I have written that one. I have already mentioned it in Word. So for those again that they like to take notes, I read it here. X equal to the y is equivalent to, this notation means equivalent. Equivalent to y is log base 2x. By the way, this one they call it base. There is a name for that. And this one is what is that. Now, we are in the form of function. And with function goes domain and range. Is that right? And domain is all permissible values that the independent variable can possess. All right? So in this case, the domain of that is all those that x can have, is permitted to be. set of all permissible values that the independent variable can have. So we have independent variable, we have dependent variable, so we are in perfect shape of what? Of a function notation. So this one is same, this is in function notation, but this is kind of is not. So that is more convenient, especially when we work with composition of functions. This is not comfortable to use in composition of function, but this one is. We will see that when we come to that. Okay, now I have a, let me see. I have a homework for you. Homework that I'm sure you can do, but for the sake of comprehending the subject much better. And that is, the homework is that select 5 or more, 5, 6, 10, whatever you select. At least 5, huh? 5 more values for x, and then determine the values of y. Very easy, huh? You can do that. You are dealing with base 2. Now, to do it this way, especially first time if you are being exposed to that, is a bit more difficult. But if you change this one to its another equivalent form of it in symbol, which is what? Which is 2 to the y equal to x, very easily you can find the values of y with respect to those values that you have assigned for x. So that is exactly one advantage of that. So when you are a little difficulty with this symbol, not a big deal. Change it into 2 to the y equal to x, because that is same as this one. Do you follow me? Again, I repeat myself, the advantage of doing this is because we will be dealing with function. And with function goes domain and range. So we know the domain of that is the input values that x can possess, and the outcome will be what? Will be our y. Okay, now the question is that I've already answered this question that I'm asking at the end, but I'm repeating anyhow. The question is that why not remain with the same notation? Why do we have to change it? I just put it in writing for the curious students that they write to write notes. I've already answered this question. No. Why do we not remain with y equals x equal to the y? Why do we have to invent another notation? So I've already answered that one. You go over that. And I have also made some example, as I already again I have mentioned that one. Like for example, the square root of x is same as x to the 1/2. Sometimes is this good to use for interpretation comes much handier than to use this symbol, depending on the equation or the whatever we are dealing with. And same is true with this one, and for of you that you are going to take calculus or you are familiar with calculus, in dy over dx stand for the derivative, and that is the notation that was invented by Leibniz. And that has a lot better application, a lot, because it has a lot of good to the interpretation of that. But this y prime was used by Newton. But in differential equation, you hardly see this notation. You hardly see dy over dx. You always see y prime. Do you follow me? But in calculus, especially first course in calculus, this notation has much more advantage to that. So notation sometimes is very important for the better comprehending the subject. Okay, then I thank you for watching, and in the next lecture I'm intending to show about the mirror image that I mentioned, y equal to x, and the proof that is the mirror. We have a good geometrical proof for that, so there is a good justification for that. Whereas rotation and reflection, there is no mathematical proof for that. We know 100% work. I give you guarantee for that. Okay then, I thank you for watching. I'm repeating that. And I wish you all the prosperity and good health. And please stay safe. So long.